Hello everyone, this is Dr. Lennon, and today we're going to be looking at the area between curves. So the idea here is really pretty simple. We want to imagine, and there's some variations on this of course, but we have maybe one curve, f of x doing something like this. So this is f of x. And then we have some other curve, g of x doing something like this. And we want to find the area that is in between these two curves. So let's say this occurs at an x value of a, this first point of intersection, and this second point of intersection occurs at some x value of b. So then the formula is really pretty simple. The area between the curves is given by an integral, and that integral is starting at a, going from left to right up to b. And it's just going to be f of x minus g of x. This is all we have to integrate, and that will give us that shaded area. In practice, usually this requires two preparatory steps. So in practice, two preparatory steps to set up the integral. One of those is you actually have to find the limits. So you have to solve for where those two curves intersect. And the other is we have to determine which graph is going to be on top. Because a lot of times you may just be given the formulas and you don't exactly know what the picture looks like right off the bat. So either you have to graph it or use some other means of deduction to figure out what curve is going to be on top. So again, these give the integration limits. And to, as we said, determine which graph is on top. So if you have intersection points, a lot of times you can just plug some x value in between and see which y value is going to end up being bigger. So that's a way you can do it kind of without graphing. But we'll see through a number of examples how this works. And sometimes we may have a picture that looks slightly different where the curves don't necessarily intersect. We're just trying to find the area from two given x values. So we'll start off with one of those such examples. So example, we want to find the area bounded by the curves. So let's say we have y equals x plus 1, y equals 9 minus x squared, x equals negative 1, and x equals 2. So, I mean, you can kind of already get a rough sketch of this if you want. I like to think about what's going on. So we have some x value of negative 1, we have some x value of 2. So these are our left and right boundaries. And then we have x plus 1, so that's going to be, this line that's doing this sort of thing. So that's another thing. And then we also have the curve 9 minus x squared. So this is going to be hitting somewhere up here at 9 and then opening downward. So we've got something doing this, something like this. So really what we're going to be shading is kind of this area right here, because we're in between the dotted lines. So in this example, the curves don't, necessarily intersect. We're just kind of looking for the shaded area between those four curves here. So we have two vertical lines, a parabola, and then a line with positive slope. So it's pretty easy. We can just set this one up. So our area here is going to be the integral starting at negative 1 going to 2. Clearly the parabola is on top, so it's going to be 9 minus x squared minus our line x plus 1. And this is the integral that we're working with. So this is the integral from -1 to 2 of minus x squared minus x plus 8 dx. And this is just the polynomial rule for antiderivatives. So it's going to be negative x cubed over 3 minus x squared over 2 plus 8x from -1 to 2. And then we plug in our numbers, and we end up with 34 over 3 when we plug in the 2, minus negative 49 over 6 when we plug in the -1, and this will come out to 39 over 2. So that is the area between those two curves. All right, so let's look at one now where we have to find some points of intersection. So B, let's say the two curves are y equals x squared minus 4x, and also y equals minus 2x. So again, here the rough picture is we've just got some parabola opening upward. And actually we know it's going to hit the, it's going to go through 0, so we've got something like this. And then we have y equals 2x. So this is, again, not to scale, but basically we're going to have some line cutting it off. So this is this curve. The parabola is on top, y equals x squared minus 4x. And on bottom we have y equals 2x. So you can find that quickly by just graphing them. So we're looking for some area that looks like that. We want to find the points of intersection. So the limits is the first thing we need to find in this example. And so we do that by setting x squared minus 4x equal to 2x. So that's where the two curves have the same y values. And then we just solve. So subtract 2x from both sides. So we have x squared minus 6x is equal to 0. And then you can factor out an x to solve. So x times x minus 6 equals 0. So x equals 0 or x equals 6. These are our two limit points. So that's the places where you see the two curves intersecting. The first at the origin and the second is happening at x equals 6. So now we're ready to set up the integral. So maybe I'll do that over here. So the area is given by the integral from 0 to 6 of, the line is on top here, 2x minus the formula for the parabola, x squared minus 4x dx. And so this is our integral, distributing that negative and simplifying of minus x squared minus 6x. Plus 6x. And again, just a polynomial to integrate, so nothing too tricky. Minus x cubed over 3 plus 3x squared. Again, just adding 1 to the power, then dividing by that number from 0 to 6. And then we can plug in both of these things. Plugging in 0 into a polynomial is going to be 0. So really that's all we have to do here is plug in 6. So we get minus 6 cubed over 3 plus 3 times 6 squared. And this comes out to exactly 36. So that is our area for this problem. Okay, so let's get into some ones that are not just plain old polynomials, a little more exotic. So let's say we have y equals x squared and y equals the square root of x. Again, if we want to think about the picture here, we have y equals x squared that looks like this. And then we have the square root of x that starts at 0 and does one of these. So y equals x squared and y equals the square root of x. And you can probably even tell without solving that these are going to intersect at 0 and 1. But we'll go ahead and write down that part anyway. So here we have the limits. We have x squared equals the square root of x. So you can solve this, I guess, by squaring both sides. So x to the 4th equals x. So x to the 4th minus x equals 0. So we can factor out an x, and we get x cubed minus 1. So we get x equals 0 or x equals 1. And again, the square root is on top there. So our area here is going to be given as the integral from 0 to 1 of the square root of x minus x squared. And again, we want to think of the square root of x as x to the 1/2 power. So when you add 1 to the power there, you'll get 3 over 2, and then you'll need to multiply by the reciprocal in front. So this comes out to 2/3 x to the 3 over 2 minus x cubed over 3 from 0 to 1. Plugging in 0 again gets rid of both terms, so this is just 2/3 minus 1/3. So our area for this problem is just 1/3. Okay, let's look at one where we have maybe some exponentials. So D, how about the area between y equals e to the x, and also y equals x times e to the x, and then maybe a third curve, x equals 0. So again, let's find the point of intersection, because what's going on here is we have x equals 0, which is just the y-axis. We have y equals e to the x. And then y equals x e to the x. We should be negative down here, below, and then above, I think. If you're not sure, we can always graph this. This one's a little more difficult to think about. It's not one of our regular graphs that we can just usually think about off the top of our head. So just to show you that, I'll go ahead and go to Desmos to graph x e to the x. Okay, so we're on Desmos. So we can graph the two curves we already have. If you want x equals 0, that's the y-axis as you can see, and then also y equals e to the x, just our normal exponential growth curve. And then we have our y equals. So this one, again, it should be negative to the left. So we should be down here, and then we should be below. And then as soon as we get past 1, we should blow by. Again, at 1, these curves should intersect. Again, we'll show that in a second. But as you can see, we kind of get the picture there. So we're looking for the area just between these two things. So let's go ahead and go back so we can kind of draw our picture there if we want. We get something like this. Y equals x e to the x. And again, we're only looking between 0 since we're starting at the y-axis. So we're really only looking for this part of the graph. Again, to figure out our remaining limits, so we know one of our limits is 0. The other one we find by setting e to the x equal to x e to the x. So now we know 0 is equal to x e to the x minus e to the x. And then we can factor out e to the x. And e to the x is an exponential quantity, so it's always positive. So e to the x can never be 0. So our answer here is just x equals 1. So we're just integrating from 0 to 1 in this example. So our area here is the integral from 0 to 1 of e to the x minus x e to the x dx. And we can split this up into two integrals. The integral from 0 to 1 of e to the x minus, sorry, I forgot the dx. dx minus the integral from 0 to 1 of x e to the x dx. And if you recall, the second integral is actually done using integration by parts. So I will let you go ahead and look that up if you forget. But this is integration by parts. You want to let u be x, and you want to let dv be e to the x. But the antiderivative, we'll write down here, the antiderivative of the first part is e to the x, and then the antiderivative after we get done using the integration by parts is x e to the x minus e to the x, and this is from 0 to 1. So distributing that negative, we actually get an e to the x plus e to the x, so that's 2e to the x, And then we also still have our minus x e to the x. And we're plugging in 0 and 1. So when you plug in 1 here, you get 2e minus e. And when you plug in 0, the first term just becomes 2, and then the second term goes away because it's going to be multiplied by 0. So we get 2e minus 2, which is just e minus 2. Which, you know, if you want, is about 0.72. All right, so that's it for this example. Again, the graph may have been a little more challenging, but really nothing was too much different. So let's go ahead and do just one more. I'll probably do a few more in a coming lecture, so we'll get some more practice. And if you have any questions or you run across any that trouble you, just let me know. You know, it is possible the more complicated the graphs are that you look at, the more difficult the integration becomes. But really, the idea here is pretty simple. You're just looking at two curves, finding their intersection, and then integrating using those limits. So one last example. Let's find the area bounded by y equals 12 minus x squared and y equals, that's a bad y equals x squared minus 6. So no different than usual. Finding the limits might be a little more challenging here, but not really too much. Just requires some factoring. Again, what's going on here? Well, I'm not even going to draw too precise a picture, but basically we have one parabola opening upward, the 12 downward, the 12 minus x squared, and one opening upward, the x squared minus 6. So we're getting something like this. So this is y equals x squared minus 6. And this one down here is y equals 12 minus x squared. So something like that, and then we're finding the area between them. So let's start with the limits. So we have 12 minus x squared equals x squared minus 6. Okay, so if you move everything to one side, we end up with 0 equals 2x squared minus 18. We can divide by 2 and get x squared minus 9. And then this factors into just an x plus 3 times x minus 3. So x equals 3 minus 3, or x equals positive 3. So those are our limits that we're integrating between. Notice the graph is symmetrical, so I can, since we're dealing with polynomials here, often it's easier to use 0 when we can. So let's make a comment here. Since the graph is symmetrical, there's two m's there. Since it's symmetrical, about the y-axis, x equals 0, we can integrate from x equals 0 to x equals 3 and double the result. So this is just one of those symmetry tricks that will make the computation a bit easier. So rather than integrating from -3 to 3, I'm just going to say the area is 2 times the integral from 0 to 3 of 12 minus x squared, the graph on top for that part, minus x squared minus 6 dx, and do it this way. So we get 2 times the integral from 0 to 3 of minus 2x squared plus 18. So this is twice minus 2x cubed over 3 plus 18x from 0 to 3. And now you can see why using 0 is optimal here. Plugging in the 0 will just make the polynomial vanish. So we end up with just 2 times 54 minus 18, which gives us an area of 72. So that's it there. So keep that in mind anytime you have some graphical symmetry. Sometimes it will behoove you to use 0 if it's the midpoint and go ahead and double that result, and it can simplify the computations. Okay, so that's it for looking at area between two curves. Again, the setup is everything here. So you want to find the limits and then determine whether or not which graph is on top between those two limits. If you're not the best at just graphing mentally or quickly, you can always appeal to a program like Desmos.com like we did for the exponential example, and that might clarify things for you. So this is Dr. Lennon signing off. Have a nice day.